Hey there, freaky nerds. In AMD's RX 9070 launch event, they talked about entering the era of path-traced visuals combined with machine learning, and the way they showed that off is with their Toyshop Demo. They say it's a successor to the Toyshop Demo from 20 years ago that ran on DirectX 9, which, by the way, is getting those fancy reflections with planar reflections. Same with on the inside there. It looks pretty good. It's not really as feasible today with today's rendering for a lot of reasons, but you'll see why that's relevant later in the video. Same with the toys and everything on the inside of the store there. We don't use planar reflections for a lot of reasons, but I think I've got a little bit of a scandal with planar reflections. At least I think I do. But here's their new Toyshop Demo, which is path traced in real time, and they're calling it neural rendering, apparently. The reason they're calling it neural rendering is because they're using this technique that they published a blog about in October of 2024, so a few months ago at this point, but they call it neural supersampling and denoising for real-time path tracing. And as they say here, it's producing the final image for their Toyshop Demo. And you're probably able to tell what it does just based on that name, but you could consider it AMD's answer to ray reconstruction from Nvidia. DLSS 3.5, people sometimes call it, which is a cool technology that replaces normal denoisers utilizing a neural network to upscale the images while also denoising it and upscaling the frame buffer. In other words, doing traditional super resolution at the same time, while also increasing the detail of the ray tracing, which includes the reflections and the lighting and the shadows and anything using ray tracing. And it works really well. You should watch Digital Foundry's videos about it if you want to know more about it. So yeah, this technique from AMD, it's new. It's a part of their GPU open, sort of open source technology / research initiative. And it's a ray reconstruction technology that can be run on AMD's graphics cards that utilizes machine learning. But I want to go back in time a little bit, because when I was learning more about this and AMD's implementation, I discovered some really interesting two papers that are really interesting and have really interesting implications, I thought. I mean, Intel released this paper talking about ray reconstruction and showcasing it a year before Nvidia released DLSS ray reconstruction. But first, I want to go back further. I want to go back to the era of the GTX 1080 Ti. I think that's almost 8 years ago, which is obviously before the RTX series of ray tracing cards. In 2017, Nvidia released a paper about ray reconstruction. Granted, it doesn't work the same way or look the same or even do the same thing, so okay, it's kind of not the same, but it is fundamentally the spiritual predecessor to ray reconstruction, and it kind of seems like the catalyst for a lot of this research, actually. This paper called Spatiotemporal Variance-Guided Filtering, Real-Time Reconstruction for Path-Traced Global Illumination. It was an Nvidia research project that aimed to bring path tracing into the realm of real-time rendering. They wanted to make path tracing possible in real time, which is very interesting. You got to remember that this is, again, 1 year before the release of their RTX series, which I guess makes sense when you think about, they would have been designing those cards for a long time, but it's just interesting to see them starting to dip their toes into trying to make ray tracing a real thing for real-time rendering, even back when the GTX 1080 Ti was their card of choice. Because yes, the GTX 1080 Ti was released 5 months before this paper was released. But yes, they say this technique can achieve stable images as long as you're running above 30 FPS. The difference between this and ray reconstruction, the practical difference between this and ray reconstruction, is that this does not upscale the image. It renders at native resolution with 1 sample per pixel, and it denoises the output from there. But the denoising of the ray tracing kind of, when you're running at 1 sample per pixel and you're accumulating it, kind of is upscaling it still. But anyway, this technique from Nvidia does not use AI. It's not a machine learning model, which is really interesting. Nowadays, Nvidia's entire thing is ray tracing along with AI and combining the two. So it's interesting to see kind of the ways they were exploring these things without using AI, or without using specific ray tracing cores even, I might add. This is running on shaders, which is why they want to render at 1 sample per pixel, because ordinarily in path-traced rendering, to get a reference image, you would need to render 2048 samples per pixel, according to Nvidia. So that's reducing from 2048 to 1 sample per pixel. So obviously a dramatic decrease in compute time there, especially without ray tracing cores. I guess they're saying it's a lot more efficient than sampling 2,000 times per pixel. But anyway, since this is not AI, it can run on less powerful hardware since it doesn't need to run an AI model, and it doesn't require any special acceleration or hardware features or upgrades or new graphics cards. It can be implemented on existing GPUs. And there's a video with this paper. Here is the raw, unfiltered 1080p 1 sample per pixel image that is being passed into the algorithm. And then here is their technique running. So a big improvement, obviously. You can see a giant improvement. Oh my god, who's this? Anonymous Pumpkin just came into the document. My document that I've been writing to reference all this information that I'm linking in the description. Whoever Anonymous Pumpkin is, you're in the video. But anyway, okay, here again is the unfiltered image. And I did notice some artifacts though with this technique, obviously, particularly in the reflections, or I believe as they would call it, specular global illumination is what they would call it in the paper. But on these reflections here, on these windows, it's more obvious over here. There is it's more obvious on this window on the left here. There's a significant amount of boiling in the reflections, which is very understandable. You know, they look really cohesive, so. But just an interesting note, because it is a common running theme with all of these techniques, so-called boiling artifacts. And just real quick, they compare it to the other state-of-the-art techniques at the time for denoising real-time path-traced images. And so here they're showing some spatial-only filters, which mean they don't utilize any previous frames. They're just looking at the current frame. That's the only info they get. And as you'll see, they're very noisy. So that's not terrible. That's not very good. That's okay. So, but they're all very noisy, obviously. Now here is their technique that they're showing off. Looks, wow, very stable. And then they show what it would look like without the temporal part, without the previous frames. Which is interesting. And then they show it with the other frames. You can definitely still see a little bit of boiling in the shadows in the global illumination. Up here in the top left, where not many rays are reaching. But it's really, you know, pretty good overall. Here's one more test they show, which is the shadows. So here's the previous techniques. And then here's theirs. Here's previous techniques. Here's theirs. It looks a lot better. But now, building on the work of Nvidia's non-machine learning research, Intel in 2022, which again is a year before DLSS ray reconstruction was announced, Intel released their own ray reconstruction paper, but this time utilizing machine learning. And they even compare it directly to Nvidia's paper that we were just looking at. This left image here that shows the technique we just looked at, Nvidia's SVGF. In the middle, it shows Unreal Engine 4's default denoiser. And then on the right, it shows Intel's ray reconstruction running. It's definitely a much more subtle difference. It's not as obvious. The difference between these two is not as obvious unless you're zoomed in. But as you can see here, there's a lot of ghosting, a lot of blurring around the movement here, and the reflections do not look very stable with the Unreal Engine one. And then the Nvidia one is just very blurry, doesn't look very good, but that makes sense. It's much older. You can really tell in the Unreal Engine one that it's very ghosty and noisy, and there's lots of speckles everywhere. Some of the details in the reflection is being smeared over. You can't even really see that there's some there. And yeah, the reflections look kind of noisy. And with Intel's ray reconstruction here, you can see it looks very clean. There's even more objects appearing in the ray tracing, it seems like. I mean, I couldn't even tell those little things were there. and they compare it directly to Nvidia's paper here. You can see Nvidia's paper is really smeary, and they compare it to Nvidia's paper that we just looked at here, Nvidia's SVGF technique. And as you can see there, even compared to the Unreal Engine one, it's kind of blurry, very blurry and smeary. There's even more ghosting in this one actually, but that makes sense. It's a much older technique. But talking more about the paper, Intel makes it clear that enhanced denoising techniques are essential for real-time ray tracing. They claim that ray tracing in modern games results in undersampling, and how previous techniques tried to address the issue of denoising and upscaling separately, and while also highlighting the challenges of neural denoising. But yes, here's another comparison that they show. In this one, they compare XeSS upscaling with Intel's ray reconstruction, because the way the XeSS is upscaling is it's using Unreal Engine's default denoiser, and then it's upscaling with XeSS. Holy shit, we got Neon Cat. Oh my god. But you can see, especially on this chair here, that compared to Unreal Engine's denoiser running with XeSS on top of it here, there's a lot more texture detail coming through with their ray reconstruction technique. Along with this text here, the text is more readable, a little bit less blurry than the XeSS upscale with the default denoiser. Here you can see they're comparing Unreal Engine's default denoiser running with XeSS on top of it compared to Intel's ray reconstruction technique that they're showing off. You can see here on this chair a lot more texture detail coming through. And on this text up here, you can see it's a little bit more legible with less blurring. And when I zoom in here, you can see that although the XeSS one looks pretty sharp, it's also pretty noisy and generally doesn't look as good. And I would say it looks worse than the ray reconstruction one. And again, you can even see a little bit more detail coming through there with the ray reconstruction. Along with down here on this reflection, it's blocky with just XeSS running. But I will say there's some parts about the image that are better using the XeSS upscale. So that's interesting. Like this texture detail specifically looks better with XeSS. But then other texture details like this one here on this chair, obviously, and then this tube looks better with XeSS. But anyway, so that's not really to say that the ray reconstruction's bad or anything. It's just interesting to note. But anyway, I thought it was really interesting that Intel released this paper before Nvidia. But at the same time, in the paper, I think they said that they were using an RTX card, that they were running it on CUDA or something like that. So yeah, anyway, just funny that they're using an Nvidia card. And then it's also building on top of Nvidia's research too. But then finally moving on to the present day again. AMD's new neural supersampling and denoising for real-time path tracing. Based on this paper, this technique seems very similar to Intel's technique that they showed off in the paper. They're both machine learning models that are designed to denoise images while also upscaling them. And AMD is actually showing it off in a demo. Unlike Intel, which I don't think released any demos or public demos of it, but AMD is utilizing it for their Toyshop demo, like I said. AMD talks about in the article how even if you cast several thousand samples per pixel, it can still fail to converge on a high-quality image, and there could still be visual noise. And so AMD's claim is that denoising is needed, no matter the sample count. So AMD's claim is that pretty much no matter what, you need denoising for real-time path tracing especially. They talk about how neural denoisers are getting a lot more attention recently, but then they also reference, midway through, they specifically cite Nvidia's paper right here when talking about how they fall short in image quality, which isn't really actually a jab because it's a 7-year-old paper from Nvidia. Because it's a 7-year-old paper, which is a shit ton of time in computer graphics and even longer in AI research, which, especially when you consider that time frame of 2017 to 2025, that's like an explosive time for AI. So really not fair. Really not fair to criticize Nvidia at all for that. Just thought it was interesting that they would do that. I just thought it was interesting that they would be that direct, but it's not really, like I said, it's not really offensive. And yes, they also reference Intel's paper right here. But I wanted to talk about some specifics of the Toyshop demo because I have some observations. Now, AMD showed this demo off at the 9070 event. AMD showed this demo off at the RX 9070 event. It features fully path traced lighting. So it's path tracing the shadows and the reflections and the global illumination, which includes the ambient inclusion. And it also utilizes two established techniques in ray tracing called ReStir and neural radiance caching. Neural radiance caching basically increases the effective number of bounces that each ray has. So instead of having each ray that you shoot bouncing around the room 6 times, you might only need to bounce it 2 times, and they use a neural network to cache previous data along with using it for predicting, for somehow kind of faking extra bounces from a ray that you didn't actually have to trace. So it's interesting. I don't fully understand it, but it essentially allows you to achieve better performance by not having to bounce the rays around as many times and still getting the image quality of multiple bounces, like reflections in reflections, better global illumination, other things like that. And they also use something called ReStir, and that basically changes how it decides to shoot rays. It makes much better use of the rays that it does shoot, and it's able to decide which rays to trace a lot more effectively. It's able to decide which rays to trace and where to trace them a lot more effectively than just randomly sampling, which is what they would do without ReStir usually. So basically ReStir increases the effective sample count because the rays that you are tracing are a lot more significant, and it's a lot more intelligently decided which rays to trace. Those are two techniques that are already well established, as far as I'm aware. They're already used in games like Cyberpunk, stuff like that. I hear Alex from Digital Foundry talk about it a lot. I never really understood what it meant. But the new thing that AMD is adding on top of that is their neural super sampling denoiser, which again they talk about in this article here. And they demo it with this cute robot guy working on his friend. But this is really helpful for understanding how the ray tracing works. So here's the normal path tracing with random sampling, presumably 1 ray per pixel, something like that. And then they show what it looks like on top of that, adding ReStir. So this is again changing how you sample the rays to be more effective with each ray that you shoot. So you effectively get a better looking image with the same number of rays. And then they show adding on top of that their neural radiance caching, which is another neural network that remembers previous hits on the ray tracing and previous rays, which again is increasing the effective number of bounces that you're getting in things like reflections or in global illumination. And again, you can see that right up here in the reflection in the top. You're able to see there's some black spots here, or just some spots where it seems like some parts of the image aren't fully being represented in the reflection, or maybe that there is incomplete global illumination around these paint cans, and that's from the rays only being allowed to bounce around the scene maybe twice. So they add on top of that neural radiance caching, and that adds in additional bounces there, additional effective bounces, and then they show on top of that adding their neural super sampling and denoising technique, which is a lot like ray reconstruction. And obviously it looks a lot better than that raw path traced image. It's got some, AMD says that there's 1 million dynamic lights in this scene, so that's a lot. And it's a pretty cohesive image, it doesn't look noisy, and it looks like it's got some pretty advanced lighting effects. But I also have some problems. First of all, as I've seen a lot of people point out, because it's very obvious, the specular reflections on this table here with this little glowing thing, very noisy. You can see it's boiling there again, just like with the Nvidia SVGF paper, lots of boiling on the reflection on the desk there. And you can even see it in some other spots that are less obvious. For example, this robot's feet up here, you can totally see it. And there's lots of places that you can notice it if you look close. Not a lot of rays are reaching that spot, and so there's noticeable boiling in the image. But overall, like this right here looks great. but there's more going on still. When I first saw this scene, I was surprised. I was like, oh, that mirror looks very clean, you know? It's not boiling or anything like that. But then I thought about it a little more, and then I noticed the robot is not reflected in the specular reflection on the table at all. And neither is that moving blimp thing. You can see it especially in my document here, that this blimp is not appearing in the table's reflection really, and especially the robot guy. You can see in my paper here especially that the robot guy, he is not appearing in the reflection, even though he's hovering directly above it. And the same goes for the blimp, but it's a little bit less obvious there. But then I went back and I noticed that on this other little toy robot thing, that he's not really reflected in that either. And at first I thought, oh yeah, he is, you can see it, but that is not a reflection of him. Something is moving, something is changing in the reflection, but it does not really represent him. It doesn't seem like, and it seems like it's a screen space reflection, if you ask me. I think that really resembles a screen space reflection. Maybe it's just he's moving too fast, that it's too noisy and it's not denoising it well, but to me it definitely seems like the robot, this dynamic object, is not represented in the BVH structure. And so he doesn't appear in the reflections on the desk there. Neither does the blimp flying around. And he also, it's harder to tell if he's affecting the global illumination or not. His light on him is. But yes, this mirror here, I'm almost positive that this mirror is some kind of rendered to texture or planar reflection, because it does not resemble the specular reflections on anything else. You know, it's perfectly clean. It looks like native image quality. There's no kind of ghosting in it. It obviously can't be a screen space reflection because you're seeing parts of the scene that you can't see in screen space, but it doesn't look anything like the rest of the ray traced reflections. And there's a lot of specular objects in the scene. So the fact that the mirror looks so different from the rest of the specular reflections, and that the robot guy doesn't appear to be represented in the specular reflections, and the fact that that's a common optimization used for ray tracing titles, I think that that just makes sense, obviously. It's a little bit strange to see with a quote-unquote fully path-traced demo, but I would like to see a future where path tracing and ray tracing includes dynamic objects without any problems. But yeah, I mean, I guess it makes sense. It's the BVH structure is a part of the ray tracing that needs to be updated every time something changes. So it would be very expensive, I guess, to have this dynamic object be part of the BVH somehow. So it's a logical optimization, but I thought it was a little bit misleading to put this mirror here so directly with this tag here that says real-time lighting and reflections. I mean, it is real-time, it's just the mirror is not a ray-traced reflection or a path-traced reflection. It's a classic planar reflection. So, just interesting. In the rest of this demo, I mean, a lot of people have already pointed this out. In the rest of this demo, I mean, there's a lot of ghosting, to be honest, and a lot of smearing. Right here, you can see it's pretty obvious. But I think this demo is still actually really cool and a significant step forward for AMD. Those reflections, for example, that's what I don't get. Okay, those reflections on the windows have moving objects like those lights in them. But maybe lights are able to be represented in the BVH easily. That's my assumption. That like lights, like on those cars, can be traced easily without having to have the cars themselves actually be in the BVH structure. So I think that, yes, those lights are probably dynamic and being path traced, but the car's geometry themselves is not. So this part here, yeah, it kind of looks smeary. It's weird. It's weird looking. And you can see the specular shimmering on his face, kind of. But it's a fully path traced demo in real time from AMD. I'm happy to see it. I know I'm being critical, but I'm just trying to be fair. I just want to see them succeed. So yeah, overall, I thought this demo was a really interesting showcase with many ups and many downs. There's a lot of mixed feelings, it seems like people have very mixed feelings about this demo. I mean, generally people are really happy about it, and I think people like it, and they're glad AMD made it, but at the same time, it's pretty easy to criticize the flaws that are there. But I think you could also say that AMD isn't trying to hide anything from us, and that they're being very honest, except for with the mirror thing. I don't agree with that. Just don't put it in. You don't have to pretend there's this perfect ray traced reflection, but it seems like they're really trying to get people to think that this is a ray traced reflection. And maybe I'm wrong. I don't think it is, though. All the other reflections, like on the desk and stuff, it is. Those are ray traced or path traced, but the robot guy is not a part of the ray traced reflections. But yeah, I think that's an interesting neural rendering demo for AMD, or at least the extent of their neural rendering for now. I'm going to do some research and make another follow-up video about any other possible other potential answers to neural rendering that Nvidia has for things like their RTX Faces or their neural materials / neural texture compression system thing. All the neural rendering stuff that Nvidia showed off that wasn't just their ray reconstruction or their neural radiance caching or ReStir. But for now, I think, yes, that's where I'm going to leave it for talking about AMD's ray reconstruction. I'll do some more research, see what I can find out about my predictions for the future of AMD's technologies. I'm a little too tired right now to do anything profound. But yeah, check out my other videos if you haven't seen them, talking about FSR4 running on RDNA 3 cards with its potential FSR4 Lite model, and these other papers talking about CNN transformer model hybrids about 3 years ago, which is pretty interesting. So that's been a growing technique that AMD decided to adopt for FSR4. I would still like to go a lot more in depth than I went in this video on some of these topics. I feel a little bit like I skipped over some stuff I wanted to say, but I think I said everything important. But yeah, I'll see you guys in the comments, hopefully. I really like having discussions in the comments and figuring stuff out. So I'll see you guys later. Peace.